Okay. In the previous class, we stopped with this exercise question and asked all of you to think about this and, if possible, try to solve this. Today, we are going to look at the solution. So the question, let me repeat that. So you have 5 devotees who started, this religion of Blue Goddess. And what they do is that on the first day, they will preach to one new recruit who will join. Okay. Now, everybody who gets converted do the same thing that, in the next morning, they will preach to exactly one new person and he will also join. Now, from second day onwards, for every person, after he joined, the second morning onwards, they will recruit 9 new people, and all of them, once converted, will be the devotees forever. So, if that is the assumption, how many devotees will be in the religion of Blue Goddess after the nth day? That is the question. So, as we saw in the previous case, we can try to come up with a recursion and then try to solve the recursion using generating functions. So, what is the recursion? So, what are the initial conditions? We can immediately see that the 0th day there is exactly 5 people, and on the first day, because each of them have recruited exactly one person each, we have 5 plus 5, which is 10. So we know that if dn counts the number of devotees after n days, then d0 is 5 and d1 is 10. So the question is that what is the recursive formula? So maybe you should think about this. What is the recursive formula? Because sometimes coming up with the recursive formula can be a little tricky, but in this case it is not very difficult. So let us see. So first of all, what we note is that if you look at the nth day, right? So whoever has joined in the n-1th day will recruit one person each, right? So in fact, everybody will recruit at least one person on the nth day, right? So whoever was there in the previous day, that many people will be always recruited on the nth day. So if if you are looking at dn, then we definitely have 2 times dn minus 1 people. But now those people who have been for even at least one more day, right? Which means that dn minus 2 of those people, they will recruit actually 9 people, not 1, right? Since we already counted 1 in the in the first count, then we can say that okay, they will have 8 more new recruitees. So that is why we will get the following recursion, that is dn is equal to 2 times dn minus 1 plus 8 times dn minus 2 for n greater than or equal to 2. Okay. So now once you have this, how do we continue? So well, that is easy, because we just take summation n greater than or equal to 2 dn x raised to n, right? Multiplying with x raised to n equal to 2 times summation n greater than or equal to 2 dn minus 1 x raised to n plus 8 summation n greater than or equal to x raised to n, right? So this is what we get. Now what is here is basically, except for the first 2 terms, you have the entire generating function of dn, which is, let's say, d of x, right? So d of x is the generating function. Then we have the first 2 times missing, right? So which means that we have to subtract d1, which is in our case d1 is 10, right? Minus 10 x, and minus d0, which is 5, right? Now this is equal to 2 times there is an x which is additional, you can take it out. So then you will get except for the first time, you will get the generative function, which is 2x times d of x minus the first term, which is 5. Right? Then if you take 2, so here it's n minus 2. So if you have if you take 2 x, which is x square outside, so you have 8x square, then the generating function, right? So that is the d of x. So now you can collect d of x together. So you have d of x into 1 minus 2x minus 8x square is equal to 10x and 10x cancels. So you have minus 5 which comes here is equal to 5. So therefore we have d of x is equal to 5 divided by 1 minus 2x minus 8x square. Now this denominator seems to be easily factorable, right? So we have AB is this thing and I plus B. So therefore it's basically 5 divided by 1 plus 2x and 1 minus 4x. Now you can write this as, let's say, alpha by 1 plus x or 1 plus 2x plus beta by 1 minus 4x. So this is the standard procedure. Now if you solve for alpha and beta, then you will get alpha is equal to 5 by 3 and beta is equal to 10 by 3. You can work it out. So then you have the generating function in this form, that d of x is equal to 5 by 3 into 1 by 1 plus 2x plus 10 by 3 into 1 by 1 minus 4x. So now it is easy. If you want to get the coefficient of x raised to n, all you have to do is pull it out, right? So x raised to n d of x is equal to, so 1 plus 2x, right, whole raised to minus 1. So therefore this is basically minus 2 whole raised to n, right, the nth time. So 5 by 3 into minus 2 whole raised to n minus 1 whole raised to n and 2 raised to n, right, plus 10 by 3 into 4 raised to n. So you will get the formula for dn, right, which is dn. So this is dn. Now we can verify whether what we computed is correct by checking what is d0, d1, d2, etc. Right. So what is d0? D0 must be equal to 5. So let us see what is n is equal to 0. You will get these two to be 1. So 5 by 3 plus 10 by 3, which is 15 by 3, which is 5. Right. So therefore d0 is 5. What is d1? d1 is equal to, so this is 2 into minus 1. So I have 10 minus 10 by 3 plus 4 into 10, 40 by 3, which is minus 30 by 3, which is 10, right? Plus 30 by 3, which is 10. And that is also correct. So we can hope that our calculations are correct. Recall that the Hemachandra numbers, also known as Fibonacci or Hemachandra Fibonacci numbers, satisfies the recurrence relation Hn is equal to Hn minus 1 plus Hn minus 2 for every n greater than equal to 2, with the initial conditions H0 is 0 and H1 is equal to 1. Now, in some places, you might see h0 also defined to be 1, which will only result in a shift of the position in the sequences that we compute. Other than that, remains the same. Now, we proceed in the using the same ideas that we have, but we will look at it in a slightly different manner. So we start by defining the generating function of the Hemachandra sequence as h of x is equal to summation hn x raised to n. Then what we do is that we know that the sequence satisfies the recurrence relation that we looked at before. So therefore, what it says is that if you take hn and subtract hn minus 1 and hn minus 2, you should get 0, right? Because of the recurrence relation. So that's what we are saying here, that if you look at h of x, the coefficient of x raised to n in h of x minus x times h of x minus x squared times h of x, what we are actually saying is that this coefficient is basically n. This is hn minus 1 because we are shifting the power by 1, and here we are shifting by 2, so this is hn minus 2. So what we are saying is that hn minus 1 minus hn minus 2 is equal to 0. Now this is for all n greater than or equal to 2. Now if that is not the case, then what are the other cases? N is either 0 or 1. So what happens if n is equal to 0? So well, if n is equal to 0, you can see that h of x there is no constant time, and in this also there is no constant time. So the only constant time is going to be in here, and the coefficient of x 0 there is basically h0 itself, which is 0. Similarly, the coefficient of x that is appearing is in h of x there is 1, and in which is basically h1, right, h1x, and here h0 becomes h0 times x, so therefore that is also there, but here there is no time with x, so therefore you have h1 minus h0, right, from this, and that is basically 1 because coefficient of x raised to 1 is so this is 1 minus 0, which is 1. Now these three together gives the entire equation h of x minus x times h of x minus x squared times h of x, right? Because you can just add them together because each three cases are there. So therefore you can see that this is basically equal to just the coefficient of x, right? Because this is 1 is a coefficient of x, and everything else is 0. So therefore you will get x. So so now you get the equation for h of x. So you take h of x outside, you will get h of x into 1 minus x square is equal to x. So therefore h of x equal to x divided by 1 minus x square. So to solve this, is easy. That it's a quadratic formula. You can either use the b square minus 4ac method, or you can just observe that if you write it as 1 minus alpha x and 1 minus beta x, then it should give you alpha plus beta is equal to 1, and alpha beta is equal to minus 1, right? And from these two again you can verify that alpha is equal to, we can compute that alpha is equal to 1 plus root 5 by 2, and beta is equal to 1 minus root 5. Now once you compute this, then what remains is to write x by 1 minus alpha x and 1 minus beta x, right? This is equal to something over 1 minus alpha x plus something over 1 minus 1 minus beta x. This is, you can just work out the details as we did in the previous cases, and you should get that this will be equal to 1 by basically alpha minus beta into 1 minus 1 by 1 minus alpha x plus 1 by minus 1 by 1 minus beta x. Okay, so this is something you can work out. And once you have this, what is 1 minus 1 by 1 minus alpha minus beta? Alpha minus beta is basically root 5, right? So basically what you will get is that it's equal to, maybe I can write in the other page, 1 by square root of 5, and then 1 by 1 minus alpha x, right, into 1 by 1 minus alpha x minus 1 by 1 minus beta x, where alpha and beta are as we defined before, right? 1 plus root 5 by 2 and 1 minus root 5 by 2. Now, from this you can read out the coefficient of x raised to n, right? So, if you want coefficient of x raised to n from this, right? 1 by root 5, I write it again, right? 1 by 1 minus x minus 1 by 1 minus beta x is precisely 1 by square root of 5 into 1 minus alpha x. 1 by 1 minus alpha x should give, in the power x raised alpha raised to n, right? And minus beta raised to n, right? So you have alpha raised to n minus beta raised to n by square root of 5. So what you are saying is that this is basically 1 plus 1 plus square root of 5 by 2 whole raised to n minus 1 minus square root of 5 by 2 whole raised to n. So 2 we can take out if you want. So we'll get 2 raised to n here. 1 by 2 raised to n square root of 5. 1 plus root 5 raised to n minus 1 minus root 5 raised to n. And this must be an integer because we are counting the Fibonacci or Hemachandra numbers, right? So therefore, these are it's surprising that something a formula like this will give you always integers. So that is it. So we have solved the Hemachandra recurrence, and we have our solution. Now what else? So here is a couple of homeworks for you. So use generating functions to solve the following question. So you are given that there are 50 lotus flowers are thrown into a magic lake. So the lake is magic in the sense that if you put some lotus flowers there, next day, right? If you look at that, you will have 4 times the number, right? If you put 50, then you will have 200, right? If you have 100, then you will have 400, etc. So every day the number of flowers grow by 4 times in the midnight. Now in the morning, what they will do is that they will go and collect 100 flowers for selling. Now after 30 days, how many flowers will be remaining in the lake, right? After n, I should have written days, not years, right? After days, after n days, how many? So this is just n. So can we find a formula for this? That is the question. Now second question is that let bn plus 2 is equal to 3 times bn plus 1 minus 2 times bn is a recurrence relation that is given. And with the initial conditions, I'm making so many mistakes. That b0 is equal to 0 and b1 is equal to 1. Okay, so these are the initial conditions. Find the generating function b of x for the sequence bn and hence deduce an explicit formula for bn. So this is the second question. And another question is that given a sequence, let's say fn n greater than or 0, that satisfies the following requirements. Okay, so k plus 2 choose 2 is equal to summation I equal to 0 to k fi into fk minus I for every k greater than or equal to 1. And the initial condition is that f0 is equal to 1. Now find the generating function f of x and deduce the formula for fn and use it to compute, let's say, f4. So these are your 3 homework questions. Now we look at, so we already know, we have looked at the product of two generating functions. Now we want to see how this product makes sense combinatorially. So combinatorial meaning of the product. So suppose an and bn denote the number of ways two different combinatorial structures on sets of cardinality n can be made, right? So you have two combinatorial structures, let's say a and b, and an is the number of ways to make structure of type a on an element set, and similarly bn for the type b structures. Now cn is the total number of ways, okay, to first build a structure on type a on some set, let's say 1, 2, 3, etc. I. Okay, so you basically split the set 1 to n into two intervals, 1 to I and I plus 1 to n. Okay? And on the first interval, right, 1 to I, you make structure of type A. And on the second interval, t, which is I plus 1 to n, you make a type B structure, right? This you can do for each I, right? I ranging from 0 to n, right? Which means that the interval can be empty also. So then suppose a of x and b of x are the generative functions, and c of x is the generative function for the third cn, then show that c of x, then we claim that the theorem says that c of x is equal to a of x into b of x. Okay. So basically, the product of the generative functions represent the sequence that you obtain by this procedure. Okay. So basically, the product of generative function means that you have two structures a and b, right? So you make the structure of type A on 1 to I for some I, and from the remaining elements you make type B structure. So how many ways, different distinct ways you can do this? That is the meaning of the product. So how do you prove this? Well, this is easy to see because see, if you look at what is Cn, right? How can we get Cn? So you are basically saying that you make on an I element set, you are making a type A, which means that there is ai possible ways, right? Then on an n minus I element set, you are making a type B structure, which I can do it in b n minus I possible ways, right? And what else you have? Well, you can change I from any of this, and in fact, if you fix an I, then the number of ways you can do here and number of ways you can do, these are independent, right? You make any structure that you want here, you make any structure you want on the B type, on the n minus a element set independently, so therefore I can multiply them, right? And I can select any I because I can range from 0 to 0 to n, right? So this is the total number of ways, right, I can produce these two structures given an n element set. So therefore, the coefficient Cn is basically this, and that is what the coefficient of x raised to n in this product by the product formula that we have studied before, right? Summation ai into bn minus I. So therefore, that is the proof. Okay, so I'm not writing anything further, but you can see that it can be completed. Okay, now let us see an application. So here is a problem. So there is a short course that is going to be run on combinatorial algorithms. Okay. Now the duration of the course is n days, and out of this, so the teacher decides, let's say first k days will be basic combinatorics, and the remaining n minus k, of course, days will be for algorithms. Now out of the first k days, one day you will choose to be non-instructional day. Okay, so one day will be holiday. So that is must. Then from the remaining n minus k days, 2 days must be chosen for labs, because you are studying algorithms. You will have some labs. Okay, so 2 days will be for labs. So that is also necessary, that you need to have 2 days for the lab. Now then the question is that how many ways can this semester be planned, right? So what we are saying is that your k can range from, k should be at least 1, right? Because you need to have at least 1 day to be decided as holiday, so that cannot be avoided. And then so k should be at least 1, and then you should have at least 2 days for the labs, right? That is also important, right? Even though there is no theory, you should have lab. So therefore you should have at least 2 days remaining after you take away k. So therefore you can can range from 1 to n minus 2. Okay, so therefore 1 is less than or equal to k less than or equal to n minus 2, and then define Cn to be the number of ways the course can be planned. Okay. So one can immediately see that by our earlier look at the product relations, we can see that you can independently choose the one of the k days as holiday, and from the remaining n minus k days you can choose any 2 days as your lab days, right? So k into n minus k, choose 2 possible ways you can do this, and k ranges from 1 to n minus 2 as we said, and therefore you have all these possibilities. So therefore Cn is precisely this. Now the question is that if you want a closed formula, how does this reduce to a closed formula? It's not very immediate. So therefore we can try to use generating functions. Okay, so we observe that we can independently calculate for the first days for the combinatorics and the holiday selection, and you can find the generating function for that itself, and for the remaining selection of 2 days from the remaining n minus k possible day, right? So n minus k plus k is going to be n, and therefore for any choice of k, right, ranging from 1 to n minus 2 is okay. So therefore we can use the product of the generative functions. So here we form the generative functions, right? So for each k, there are k ways to plan the combinatorial course, with one holiday, right? You fix one of the k days as holiday. So therefore, exactly k possibilities for that. Then denote by ak as the counting sequence, right? So what is the counting sequence? Well, because ak is k, a of x is basically summation k greater than or equal to 1, k times x raised to k, because k is at least 1. Now, similarly, you can define, let's say, BL to be the L choose two ways to plan algorithms with two labs where L is equal to n minus k, right? If you have L days available, then out of this, you can select 2 days for the lab in L choose two ways, right? Any of the 2 days are okay. So, therefore, now B of x, right, is basically summation L greater than 2, because L is at least 2, L choose 2 and x raised to L. Right? This is also clear. Now, once you have these two, what you do, you find A of x into B of x, right? Or you first resolve for A of x, right? So A of x is, you know, you can write take one x outside, so you can see that is basically k greater than or equal to 0, k plus 1 into x raised to k, which we already solved and said that this is basically, the derivative of the geometric series, right? So this is the derivative of the geometric series, so which is 1 by 1 minus x square, right? So therefore, I have x outside, so x by 1 minus x square. So a of x is simplified to this. Then b of x is basically summation L choose 2 into x raised to L. And I take, let's say, 2, power 2 of x, right? X square outside. And by 2 from here, L into L minus 1 by 2. So if I take it outside, I will get summation L greater than or equal to 2, L into L minus 1, x raised to L minus 2. Now, this, if you remember, right, is is the second derivative of the geometric series, except for there is a factor of 2 will be coming here, that 2 can come here. So that is the idea. So you have 2 by 1 minus x cube here, right? So what you will get is that b of x is equal to, so this x square times this summation is 1 by 1 minus x cube, and therefore you have this as your b of x. I mean 2 by 1 minus x cube. This is 2 by 1 minus x cube, and this 2 cancels out. So you'll get x square by 1 minus x whole cube. So b of x is this, a of x is this. So multiplying this, I will get c of x as x cube divided by 1 minus x whole raised to 5. Now all it remains is to take out the coefficient of x raised to n, right? Now, of course, there is a shift by power 3, right? Because x cube is sitting here. So I need to look at the coefficient of x raised to n minus 3 in this term, right? So that happens to be, if you again, so 1 by 1 minus x raised to 5, you can verify that you can take the derivative of the geometric series for times, and you will get this time, right? So this is again some small computation you can do. N plus 4 choose 4 into x raised to n greater than or equal to 0. Okay, so take this as an exercise basically to show that if you take the derivative of the geometric series enough number of times, you will get this as your summation, and then it will reduce to this form. Okay. So then because of the shift, I can say that because the coefficient of x raised to, instead of x raised to n, I want x raised to n minus 3. So that will be n plus 1 choose 4 or n greater than or equal to 3, because we know that we need at least 1 for k and 2 for the labs, right? So therefore you get Cn is equal to n plus 1 choose 4. Okay. And so therefore we also show that summation k equal to 1 to n minus 2, k into n minus k is equal to n plus 1 choose choose 4. 1 second. K into n minus k choose 2. I think I missed that here. Yes. K into n minus k choose 2 is n plus 1 choose 4. So that is it. So we have found the close formula for Cn. Now let us look at the next question. So let p dash of nk be the number of partitions of n, right? Integer partitions, right, of the integer n to parts of size at most k. Okay. So this is denoted by p dash of n comma k. Then show that summation n greater than or equal to 0, p dash of n comma k x raised to n, right? The generating function for this is product I is equal to 1 to k, 1 by 1 minus x raised to I. So how do you show this? Okay. So maybe you should think about this for a few minutes and then see what you can come up with. Now, what we are going to do is basically try to expand the right side product as product of series, right? Expand the series and take the product and see what happens, and then see a one-to-one correspondence and show that. So this is what we are going to do here. So the product I equal to 1 to k 1 by 1 minus x raised to y is basically these are the geometric series, right? So 1 plus x square plus etc. Right, when I is equal to 1, then I is equal to 2, I get 1 plus x square plus x raised to 4 plus etc. And I is equal to k, I will get 1 plus x raised to k plus x raised to 2 k plus etc. Right? So this product I will get. Now in this product, what is the coefficient of x raised to n? Right? If you look at the coefficient of x raised to n, that comes from these one item from each of these k terms. So any time here will look like something like, right, 1 times t1, right? So like whatever is the degree, that is 1 times t1. Now whatever degree here is, that if you are looking at the the kth time, is basically k plus 1 k minus 1 times 2, right? So therefore it is some t2 times 2. And similarly, the third term will be some t times t3, etc. The last term will be some k times tk, right? Which position you are at. But now all of this must sum to n, because we are looking at the coefficient of x raised to n, right? So whatever is the coefficient of x raised to n, because you are getting from each of these terms, right? So therefore, that is going to be the term will be coming from this type. Now, what is this actually, right? This says that, see, what is T1? T1 is basically 1 plus 1 plus 1 T1 times, right? T2 is basically 2 plus 2 plus 2 times T2 is 2 plus 2 plus 2 T2 times, right? So if I write like this, you can see that you can visualize this as a partition of n, where the largest size is k, right? And k is appearing tk times, and 2 is appearing t2 times, etc. So this denotes a partition of n into factors. I mean n into terms where the largest part is k. Now suppose I take any partition of n in where the largest part is k. It corresponds to one time here, because whatever is that, you take the decomposition, how many times each of them appearing, you can pick that many from the corresponding bracket, right? If something is not picked, I will pick one, right? If something is picked only 2 times, I will pick the x square, right? 3 times I will pick for the third term, right? 2 times I pick from here, so etc. I will do that, right? So that way I will get a one-to-one correspondence. So therefore, you can see that this is basically partition of n, where each part is at k. Now, if you remember, if you there is also another connection that if you look at the product, the sum 1 t1 plus 2 t2 plus etc. k tk. Now, instead of looking at this as t1 1 t2 2 etc., if you look at 1 times t1 as one part, 2 times t2 as another part, k times tk as another part, right? So whatever is that number, that is your part. So in that case, you will get partition of n, because sum is going to be n, to at most k parts, because each one is basically the number that you are looking at. So therefore, this should also be in bijection with the thing, right? Because this defines a partition where the partition of n into at most k parts. So we see that the observation that we had looking at the Farage diagrams, right? By the rotation, the flipping of the conjugate of the Farage diagram, that there is a one-to-one correspondence between the partitions into at most k parts and partitions of size at most k. You also get a proof here, right? Now, as a corollary to the result, we can say that, like, see, for at most k, we are doing 1 to k. So if you don't put any limit, you can put 1 to infinity. So all possible partitions will be product k equal to 1 to infinity, 1 by 1 minus x raised to k. So that is the generating function for Pn, right? Partitions of n, right? All possible partitions. So, okay. Now, a couple of homeworks. So the first question is to show that the generating function for p of n comma dist of the partitions of n into distinct parts. Okay, so I denote by p of n comma dist as partitions of n into distinct parts. That is equal to p of n comma odd, where this counts the number of partitions of n into odd parts, right? Each part is odd. And then show that there is a bijection between the corresponding sets, right? Because if you show the generative functions are the same, then of course there is a bijection between the corresponding sets. So you find the generative function for each both of these and show that they are identical. Second question is, given this recurrence, Cn is equal to summation I equal to 0 to n minus 1, Ci into Cn minus 1 minus I, n is at least 1, with C0 is equal to 1 as the initial condition. Find C of x and reduce the formula for Cn as a coefficient of x raised to n in C of x. Okay, so these are two homework questions for you. Now we look at composition of I think generating functions, right? The composition of generative functions. Now let's say that an is the number of ways to build type A structures on an n element set, and we will assume that there is no construction of type A on an empty set. If the number of type A objects that you can make out of an empty set is empty. Okay, is 0, right? So therefore a0 is 0. So we'll assume that an is the number of ways to build type A structures on an element set, and a0 is 0, and bn counts the number of ways to build a type B structure on an element set, with b0 is 1. Okay, this is strictly not necessary, but we will assume that. Now let Cn be the number of ways to split the set 1 to n to non-empty intervals, right? Any number of them, and build a type structures on each interval, and So you take, so you split into several intervals. Each interval you make an A type structure, right? And then build a B structure on the set of all intervals, right? So each interval you consider as one element, and then you make out of these intervals you make B structures on that. Okay. And now if A, B, C are representing the generative functions, right, where C is the generative function for the number of ways to do all these things together, right? Then C of x is equal to B of A of x, where you substitute the variable of B with A of x. So the proof sketch is follows. So the number of ways to build type A structure on k disjoint intervals, right? We are suppose for some k, we are putting into k intervals. What is that? So by the product formula, right, for given an arbitrary set, right, whatever is the number of elements, it should be given by A of x, right? So that is represented by A of x. Now, if you want to find out for k disjoint intervals, you take A of x whole raised to k, right? Take k times product, k-fold product of A of x. That should give you the distinct ways to do this, independently for each of the k intervals, right? Now, once you do that, you get these objects, right? Take these objects as elements, and then you build a B structure on the k element set. Now, for this k element set, you have bk, right? That is the definition of bk, right? So, given a k element set, you have B structures you can make is exactly bk. And these are independent, so therefore I can multiply. So, bk into ax raised to k, right? This is the term. Now you can sum overall k. So therefore summation k greater than 0 k into ax raised to k, which is the definition of v of a of x. So that is the proof sketch, and you get the composition formula. So here is an example. So let suppose that n people are standing in a queue. Okay, let's say to buy say Harry Potter books. Now, these people were split at several places. Okay, so there is this n people standing, and then they were split at several places, right? To non-empty cubes. Okay, smaller cubes. Then some guard from another place comes and say that okay, there is another shop where you can get the Harry Potter books. So come with me, and then he tells specifically invites some of the subsets of these intervals. Okay, so he might say that okay, I'm calling you guys, and you guys, maybe, right? And this subset he calls maybe empty. Our subsets are non-empty, but he can maybe call only some of the subQs, and maybe he don't call anybody also. That is also possible. So in this case, how many different ways this can happen? That is the question. Okay. Now, how do you do this? Well, as we can start, we define and look at AK is 1 for every k, right? What is AK? Basically, you are saying that you are splitting the intervals and do nothing, right? You are basically doing nothing. So therefore, there is only one way to do nothing. So therefore, AK is 1, right? For every k greater than 1. A0 is 0 by definition, right? We said that there is empty intervals are not there, and we cannot make anything out of the empty interval. Now, A of x is from this you can see that it is basically x by 1 minus x, because a0 is 0. So therefore I am shifting by degree 1, right? I multiply with x. So I get a of x equal to 1 by 1 minus in the geometric series. Now bk is 2 raised to k because we are saying that see if you are given k blocks, right, you can call any of the subsets, right? So how many subsets are there for the k element set? There is 2 raised to k, right? It could including the empty. So therefore bk is 2 raised to k, and therefore b of x is 1 by 1 minus 2x, right? That is the geometric series again, right? So b of a of x is now substituting for x in b, right? So x becomes a of x, which is x by 1 minus x. So 1 by 1 minus 2 into x by 1 minus x, which is 1 minus x by 1 minus 3x. Now this is 1 by 1 minus 3x minus x by 1 minus 3x. So therefore I can find the coefficient of x raised to n easily. And you can work out and show that this is actually equal to 2 into 3 raised to n minus 1 for n greater than or equal to 1. And when n is equal to 0, this will be equal to 1. You can verify that. So therefore you get the solution. Okay. So I have one more question. So n children are standing in a line, right? The line was again split at several places, and one from each section, right? The non-empty section, only non-empty sections are there, was made the leader. So each of the sections, you will select one person as the leader of his team. So this is for some game maybe, right? Now show that this number, whatever, let's denote by ln, that counts the number of possible ways to do this, is defined by ln is equal to 1 by square root of 5 into 3 plus root 5 by 2 whole raised to n minus 3 minus root 5 by 2 raised to n. Okay. And once you show this, also calculate L2, L3, L4 and L5.